Hello everybody, welcome to my channel. This video is for beginners who have started or who have finished some portion of the complex numbers and they are yet to start the geometry of the complex number, or you can say geometry using complex numbers. So in this video basically I will cover the geometry portion in complex plane, like we study geometry in Cartesian plane or we study geometry in Euclidean plane. So similarly we can also study geometry in complex plane, or you can say complex plane is also said Argand plane, Gaussian plane, etc. So uh, in complex planes what happens is that when we represent complex number in complex plane, then it is very similar to representing a point as we do in Cartesian plane, that we represent a point x and y uh, as a coordinate in Cartesian plane, or coordinate of a point in Cartesian plane. Similarly, we can express any complex number z equal to x plus iota y in complex plane as an affix of any point P. See, what is meant by coordinates in Cartesian plane? The same is meant by affix in complex plane. A double F I X, affix. We say it affix of a point in complex plane. Very similar to the coordinates of a point in Cartesian plane. First of all, let us assume that there is a complex number z is equal to x plus iota y, where x and y both are real numbers and iota is equal to under root minus 1. So iota is defined in this way: iota square is equal to minus 1. You can say iota is equal to under root minus 1. So suppose that z is equal to x plus iota y is this complex number, and x and y are real numbers. X is also called the real part of complex number z, and y is also called the imaginary part of the complex number z. But imaginary part does not mean that y has to be imaginary. Imaginary part, as you know, that it is associated with the iota. So suppose that this is a complex number and x is also a real number, y is also a real number. X is called real part, y is called imaginary part. Now let us first visualize what is complex plane. As I said, that any complex number can be represented as a fix of a point in complex plane. So let us first see complex plane. Complex plane is also called Argand plane, or it is also called Gaussian plane. Like, you must have heard the name Gauss in your physics. So similar to that, in fact the same thing, Gaussian plane. So what are the elements, what are the concepts that is associated in complex plane or that is associated in Argand plane? So very similar to the Cartesian plane. In Cartesian plane we have x-axis, horizontal axis is called x-axis, then we have y-axis, vertical axis is called y-axis, and the point where both axes intersect is called the origin. Similarly, here in complex plane, x-axis is also called real axis, or in place of x you can represent it as a real part of z. Similarly, y-axis, or you can say the imaginary axis, represented by that represents the imaginary part of any complex number z. And the points where both axes intersect is same as origin, that we call in Cartesian plane also. And suppose that z is any point that is equal to x plus iota y. And this is the point whose affix is z. Affix means the similar to coordinates in Cartesian plane. So the concept is that every complex number can be represented by a vector, or in fact you can say the position vector of a point in complex plane. And the position vector is same as the affix, as we know, as I said, that affix of a point. Affix of a point is same as coordinates of a point in Cartesian plane, or you can say position vector of a point in plane also. So instead of writing that affix of point P is equal to z, which is equal to x plus iota y, we can also say that position vector of point P, or you can say OP vector. OP vector is also equal to z. As I said, that AFFIX, affix of point P is equal to z, which is equal to x plus iota y. Now, instead of writing affix of point P is equal to z, we can also write that OP vector. See, in Cartesian plane, what we write? OP vector is equal to x, then I cap plus y j cap, right? X is called x component of the vector, y is called the y component of the vector OP vector. Similar to that, this is the concept in Cartesian plane. Similar to that, the same concept we can extend in complex plane also, that every complex number can be associated with the position vector of any point P in the complex plane, right? So in complex plane, or is as I said, in Argand plane or in Gaussian plane, OP vector can be given by x plus iota y. Instead of writing x I cap plus y j cap, like x component and y component, we can say this is real component and imaginary component, right? And modulus of OP vector is equal to nothing but modulus of z, and the form by formula we know it is under root x square plus y square. You can also derive it in the right angle triangle as shown in the diagram. So OP vector is nothing but the distance OP, the distance of point P from origin, and that is equal to mod z. In complex numbers we denote it by mod z, right? You already know this, and I just said that this lecture is more about the beginners, those who have just started the geometry of complex number, or those who are yet to start the geometry of complex number. So for them this lecture is most useful. And for those who have already studied, they can also watch this video, they can skim through the video, and whatever concept they feel useful, they can note it down in the class note or in the notebook somewhere. So till now I think the concept is clear. Similar to x-axis we have real axis, similar to y-axis we have imaginary axis, and any point P has its affix, the similar to coordinates as in Cartesian plane. Or you can say that position vector of point P, that is OP vector, is also equal to, in Cartesian plane we write OP vector is equal to x I cap plus y j cap, and in complex plane we write OP vector is equal to x plus iota y. These are the different notations. The concept remains same, the core concept is same, right? The x component, the y component, or you can say the real part or the imaginary part. So things are same, only the notation has changed, or you can say the way of expressing them or the way of studying them has changed. Now see here the angle theta. The angle theta in this case is called the argument of complex number z, or it is also called the amplitude of complex number z. As you can see, the angle theta is nothing but this angle vector OP makes with the positive direction of real axis. Positive direction of real axis. So what is the in right angle triangle we can write tan theta is equal to Pn divided by On. As you can see the diagram, Pn is the perpendicular with the base. So y by x, y and x are in fact algebraic distance. So let us put it by mod y or mod x, which will give you the absolute distance. And theta is, as I said, that theta is called the argument, or theta is called the amplitude. You can say argument also, you can say amplitude. So amplitude of the complex number z. Complex number z. So in short, it is denoted by. So let me finish writing. So argument or amplitude of complex number z. Now in mathematically, argument is denoted by, in short, argument is denoted by ARG of z, or amplitude denoted by AMP of z. So AMP of z means amplitude of z, or ARG of z means argument of z, and that is equal to theta, and that is equal to tan inverse of y by x. So tan theta is equal to y by x, so therefore theta is equal to tan inverse of y by x, right? And this is very simple formula, and you already know this because you are now studying the geometry of complex number, so you must have studied the basic fundamental of complex number. So from there, and also the zero complex number, in case of zero complex number, this argument is undefined because theta angle somehow gives the direction of the vector, in which direction the vector OP is oriented. And if you are talking about the zero complex number, which means a vector having zero magnitude, now this vector can be oriented in any direction, right? Now addition, or you can say subtraction of complex numbers using geometry, or using the geometry of complex numbers. So or you can say using the vector concept, geometry of complex numbers, so vector concept. So how can we understand that? What does it mean by z1 plus z2 in complex plane? What does it mean by z1 plus z2 in geometrically? Algebraically, it is very easy. You can just add z1 equal to x1 plus iota y1, z2 equal to x2 plus iota y2. Simply add the real part with real part, imaginary part with imaginary part. So finding the expression of z2 plus z2 is very easy. Just mathematically just add the real part with real part, imaginary part with imaginary part. But how can we interpret it, that what does it mean by z1 plus z2 in terms of geometrical concept, or how can we interpret z1 plus z2 in geometry, in geometry of complex numbers. So let us see. Suppose that in complex plane we have x-axis, or you can say real axis also. X-axis in Cartesian plane is same as real axis in complex plane, or y-axis, or you can also say that imaginary axis in complex plane. Now suppose that we have two complex numbers z1 and z2, as I have written in the screen also. Suppose that z1 is a fx of point p1, so therefore op1 vector represents the position vector of point p1, and that is equal to x1 plus iota y1. And similarly, suppose p2 is a point in the complex plane whose fx is x2 plus iota y2, or you can simply write the coordinates x2 comma y2, and op2 vector represents that position vector of point p2. Now let us draw a parallelogram drawing the parallel sides, and let us draw the resultant vector of the vector op1 vector and op2 vector. Let us say that this point P has a fixed z, so OP vector is equal to z. Simple. OP vector is equal to z. Very simple, because it is the resultant of OP1 vector, OP2 vector, or you can say z is equal to z1 plus z2. In terms of vector, you will write that it is OP vector and a fix of point P, or you can say position vector of the point P is z. So OP vector is equal to OP1 vector, you can see the diagram, plus OP2 vector. It's the resultant of OP1 vector and OP2 vector. Now what if I try to write the mathematical expression equivalent of this x in terms of x1 x2 and y1 y2. So if I assume z as x comma y, then we can write z is equal to x1 plus x2 plus iota times y1 plus y2, because just adding the real with the real part and imaginary part with imaginary part of the two vectors. So z is equal to x1 plus x2 plus x1 plus x2 plus iota times y1 plus y2. Now if I ask you to find the magnitude of z, before that we can also write z as OP vector. So OP vector is equal to x1 plus x2 plus iota times y1 plus y2. As we know that OP vector is the position vector of point P and z is the fx of point P, so both are same. Position vector of point P or fx of point P, both are same. In terms of vector, it is OP vector, or in terms of fx, it is x1 plus x2 plus iota times y1 plus y2. Therefore the magnitude of z, that is distance of point P from origin, that is equal to x1 plus x2 whole square plus y1 plus y2 whole square. If x1 y1 and x2 y2 are already known in advance, then it is very easy. Now to understand it geometrically, I have drawn the diagram and I have shown you that it is equivalent to the resultant vector of the position vectors op1 vector and op2 vector. This is very simple. Now can we write this mod z using purely vector concept? Here I have used the concept of complex number also by using the formula of modulus of a complex number. But can we find this OP vector, magnitude of OP vector, or you can say mod z, using vector concept, purely vector concept, like in terms of OP1 vector and OP2 vector? How can I write it? So there is a formula that mod, or you can also know, say that mod z square is equal to OP vector OP modulus vector OP whole square. Now vector OP is equal to vector OP1 plus vector OP2, right? This would be vector OP2, yes. So mod of this and squaring both sides. Now OP1 vector is z1 and OP2 vector is z2, so mod z1 plus z2 whole square. Now there is a formula of expanding the resultant of z1 plus z1 and z2. So the formula is mod z1 square plus mod z2 square plus yes, you can write it here, mod z square, and then plus here it is z1 z2 bar plus z2 z1 bar, right? There is a typing mistake here. It should be z1 z2 bar plus z2 z1 bar only. The coefficient 2 is written here by mistake. It should not be there. So let me correct it in the next step. So mod z1 square plus mod z2 square, and then plus, okay, first of all let me correct it. 2 should not be here, so let me remove the this redundant coefficient 2. So 2 should not be here, so only it should be mod z1 square plus mod z2 square plus z1 z2 bar plus z2 z1 bar. Now in second step I have multiplied and divided. Can I write z2 z1 bar as z1 z2 bar whole bar, right? We can also write it using the properties of conjugate. You can write that z2 z1 bar is same as conjugate of z1 z2 bar. So now this becomes real part of z1 z2 bar, because real part of any complex number z is equal to z plus z bar by 2. Now assuming z1 z2 bar as any complex number, you can write it as real part of z1 z2 bar. Now this is the formula that is used very extensively in complex number, and that is most useful formula in case of addition of complex numbers. You should remember it, and should first of all you should understand it in detail, deeply, and then you should remember the concept, right? Remember the concept. Result part you can also derive in case you forget the result. If you remember the concept deeply, you can also derive the result. This is very easy. Now how can we derive this formula? So you know this formula, mod z square equal to z bar, right? So in case of z, we can place z1 plus z2 multiplied by z1 bar plus z2 bar, right? Now I am multiplying each of them term by term. So z1 into z1 bar plus z1 into z2 bar plus z2 into z1 bar plus z2 into z2 bar. Now as we know that z into z bar equal to mod z square, therefore z1 into z1 bar equal to mod z1 whole square. Then we have, let me write the next two terms within a bracket, and then last term is z2 into z2 bar, which is equal to mod z2 whole square. So now just rearranging the terms, and we got the same result as I told you above. So mod z square, as I said, as also written in green color, you can see mod z square equal to, and here you can see that this vector is op1 vector and this vector is op2 vector. Now angle between the two vectors, op1 vector and op2 vector, let's say that this angle is theta. Let's say that angle between op1 vector and op2 vector, as you can clearly see on your screen, so I can assume that it is equal to angle theta. So it is now the angle between two vectors. Now you must be knowing that how to find the resultant of the two vectors. So it is suppose that op1 square plus op2 square plus 2 times mod op1 into mod op2 into cos theta. You already know this formula. It is very popular in vector domain. So mod z square is same as vector op whole square, and in case of vector op whole square, you can write modulus of vector op1 square plus modulus of vector op2 square plus 2 times modulus of vector op1 mod of vector op2 and cos theta. You know formula, you know this formula already in the very first class of physics, when you study the vectors and you study the resultant of vectors, how to find. So this formula is very popular to you. Now mod op1 square is same as mod z1 square, mod op2 square is same as mod z2 square, and you can write here mod of 2 times mod z1 into mod z2 into, now see, cos theta. So how can we write cos theta differently? Because in case theta is not given directly in the question, so how to find this cos theta? If z1 and z2 are given but not the angle between z1 and z2, in that case we have to slightly modify the formula, and for that let's go to the diagram to understand it. In fact, it is somehow related to the argument of the complex numbers z1 and z2, right? So you can write it as cos theta as it is for now, and let's go to the diagram first to understand how can we replace theta. In fact, theta is nothing but it is equal to argument of z1 minus argument of z2, and it is very simple to understand how theta is equal to argument of z1 minus argument of z2. Let us see in the diagram. Suppose this angle theta, and suppose that vector op2 makes angle theta 2 with the real axis, and vector op1 makes angle theta 1 with the real axis, positive direction of real axis. So argument of op2 will be equal to theta 2, argument of op1 will be equal to theta 1. This arrow diagram is intersecting the theta, it is somehow eclipsing theta. Let's remove that, let's rewrite, let's redraw the diagram, and suppose that, excuse me for a second, yes, this angle is theta 1, yes, and the angle between op1 vector and op2 vector is theta, yes. So can I write that theta from here also? You can see that theta is definitely equal to, when we subtract theta 2 from theta 1, what is left is theta. So theta is equal to theta 1 minus theta 2. So very simple. And theta 1 is nothing but the argument of complex number z1. Theta 2 is nothing but the argument of complex number z2. Very simple, very clear. Okay. So now let's go to our formula and let's see how can we, or you can simply say that theta 1 is equal to tan inverse of y1 by x1, and theta 2 is equal to tan inverse of y2 by x2. And since x1, y1, x2, y2 shall be given in the question itself, so finding theta is very easy. So now I can write theta is equal to theta 1 minus theta 2, and theta 1 is equal to tan inverse of y1 by x1, and theta 2 is tan inverse of y2 by x2. Very simple, right? So now we can write mod z square, the formula that we left above, by simply writing cos theta. So we can then replace theta by theta 1 minus theta 2, and therefore in that case mod z square shall be equal to mod z1 square plus mod z2 square plus 2 mod z1 into mod z2 into cos of, instead of writing theta we can write cos of theta 1 minus theta 2, right? And in your vector also, you know that resultant of vector a and b is mod a square plus mod b square plus 2 times mod a mod b into cos theta, where theta is the angle between vector a and vector b. Similar to that, I have tried to explain you the addition of complex numbers using vectors in complex plane. I've taught you, right, vectors in complex plane. See, vector in Cartesian plane, you know, vector in complex plane is simply the complex number itself and nothing else. So this formula is clear to you, and so I think that till now all of you must have enriched your knowledge, understood every concept in detail, in deeply. And how can we further use the vector concept? See, there are very many instances where you can use this vector concept very smartly. I'll show you many questions in the coming videos where you can use this vector concept in complex number very conveniently, and very easily we can solve even the toughest question in only few steps if you know the vector concept of the complex number in complex plane, right? And from here I'm concluding this video, and I hope that all of you have by now have understood the geometry using complex number in complex plane. There are many other things also that will be covered in the coming videos, but in this video only I have confined the contents of the lecture up to here. In the next video I'll be teaching you the multiplication of complex numbers, and merely multiplication of complex number means multiplication by any real number and multiplication of two different complex numbers. Suppose that there is a complex number z1, and this complex number z1 is multiplied by some real number k. Now how can we represent them? How can we relate the complex number z1 and k into z1 in complex plane? Like, it is very similar to the vector a and vector k into a. So as we know that same vector, the magnitude is extended, or you can say if k is more than 1 it is extended, or if k is less than 1 it is shortened, so by the factor k. Similar to that, I'll be explaining these concepts in the next video. Do follow and do watch my videos, and I can guarantee you that I'll give you all the concepts in detail, and I'll try to clear all your doubts through videos only. Okay everyone, see you in the next video. Till then, take care everyone.